Okay, today we are jumping into something that honestly sounds like it was pulled straight out of a sci-fi novel. We're unpacking an incredibly audacious academic thought experiment by researcher Juan Carlos Holland de Barcelos from the University of São Paulo. He's proposing a theoretical mega project that is just mind-blowing in scale, but the wild part is, it's actually backed up by some truly fascinating math. We are talking about the theoretical transposition of the Amazon River. So our goal for this explainer is to dig into this research, objectively look at the data the author lays out, and try to visualize exactly how on earth a monumental undertaking like this would even work. So let's set the stage with a staggering contrast. On one hand, you've got the Amazon River, literally the wettest region on Earth, right? And it's losing a massive 18 billion cubic meters of fresh water into the Atlantic Ocean every single day. Just gone. Then, on the other hand, you have Brazil's northeast semi-arid region. We're talking about 1.2 million square kilometers of land that constantly suffers from just calamitous, devastating drought. The entire premise of this research is built around solving that exact massive geographical imbalance. To truly wrap our heads around an idea this big, we're going to treat this essay like an engineering schematic and break it down into 5 steps: the water paradox, the engineering of transposition, the nuclear motor, the math of profit, and finally, environmental impacts and the future.
Let's start with Section 1, the water paradox. We're looking at the sheer scale of all that wasted potential versus the extreme need.
To put a tangible, real-world value on all that water flowing out to sea, the author points to the cheapest desalination technology in the world, which is currently used in Israel. That process operates at about 50 cents per cubic meter. Well, if we take that 50-cent valuation and apply it to the 18 billion cubic meters of fresh water exiting the Amazon's mouth daily, the river is essentially dumping $9 billion worth of fresh water into the ocean every single day. It's a tremendous loss of a highly valuable global resource. And this huge financial loss really hits home why current localized solutions just aren't cutting it. The author calculates that to fully irrigate that 1.2 million square kilometers of the northeast semi-arid region, you'd need a flow of 42,000 cubic meters per second. But the local São Francisco River, it only has a flow of 1,850 cubic meters per second at its mouth. So you would theoretically need the power of 22 São Francisco rivers just to meet the agricultural demand. Mathematically speaking, the Amazon is literally the only viable source on the continent big enough to quench this thirst without destroying existing usable water supplies. Moving right along to Section 2, the engineering of transposition. How do you physically move an ocean's worth of water across an entire continent?
You know, when humanity faces a crisis of this magnitude, like extreme regional drought or shifting climate zones, timid, small-scale solutions just don't work. There's this 2008 quote from Roberto Mangabeira Unger: "Brazil needs to stop being afraid of ideas." And that captures the exact mindset you need to even entertain an uncompromising, massive-scale engineering plan like this. The author uses this sentiment to justify exploring such a monumental, outside-the-box undertaking.
In theory, the physical engineering schematic is surprisingly straightforward. It basically functions as a massive 4-step pipeline. Step 1, you capture the water right at the Amazon's mouth, literally right before it hits the ocean, which is crucial because it means you aren't stealing water from anyone upstream. Step 2, you power massive pumps using nuclear energy. Step 3, you push that water through huge concrete pipes across a 1,500-kilometer stretch to a central hub like Petrolina. And Step 4, you distribute it to irrigate all 1.2 million square kilometers of that arid land.
Now, moving water that far is one thing, but pushing it uphill is a whole different beast. That brings us to Section 3, the nuclear motor. Powering the impossible?
So, to understand the sheer power needed here, the author calculates the physics. You're trying to push 42,000 cubic meters of water per second across a huge distance, sure, but you also have to push it up an average altitude of 300 meters to reach the Caatinga biome. To overcome that gravity and maintain the flow, it would require a mind-bending 126 gigawatts of continuous power. To put that staggering number into perspective, think about Brazil's Angra 3 nuclear plant project, which is designed to produce 1.35 gigawatts. To hit 126 gigawatts, you would theoretically need the combined continuous power output of 93 Angra 3 nuclear plants running all at the same time. The author argues that nuclear is literally the only feasible choice for this because it provides massive, uninterrupted baseload power, and over time, it's highly cost-effective per kilowatt hour compared to burning fossil fuels.
Okay, so this brings us to Section 4, the math of profit. Can an astronomical investment like this ever actually pay for itself?
Well, the author says absolutely yes, and the math points entirely to agriculture. Think about it. If you suddenly have 1.2 million square kilometers of perfectly irrigated, sun-drenched land, you can reliably achieve 3 harvests a year. Based on international market prices for staple crops, if you divided the land evenly, you could generate $504 billion in rice, $133 billion in soy, and $96 billion in corn. That adds up to a mind-blowing total agricultural output worth over $733 billion annually.
But how much does it actually cost to build the whole shebang? Breaking down the setup expenses, the largest chunk by far is the nuclear infrastructure, coming in at an estimated $252 billion. Next, you'd need roughly 38,000 massive concrete pipes, adding $1.7 billion. Finally, employing a workforce on the scale of the historic Itaipu Dam project would run about $1.3 billion. All told, the author projects a massive initial setup cost of $255 billion.
And here's where the author makes their most striking financial claim. When you take that massive gross profit from the crops and you subtract the annual maintenance and the nuclear fuel costs, you are left with an estimated annual net profit of $281 billion. Now compare that to the total construction cost of $255 billion. Theoretically, according to this thought experiment, the profits from the new agricultural output would pay off the entire mega project in under a single year of full operation.
Finally, we've arrived at Section 5, Environmental Impacts. We are essentially talking about terraforming Brazil. A project this big isn't just engineering, it's active climate modification. Now, you might immediately be thinking, wait, wouldn't this completely destroy the Amazon River ecosystem? But the calculations actually show that this massive transposition only represents 21% of the Amazon's total flow at its mouth. That means 79% of the river continues into the Atlantic Ocean entirely undisturbed. And because the water is captured right at the very end of the river's journey, the author argues it wouldn't negatively impact the upstream ecosystem at all.
Furthermore, the author hypothesizes some really fascinating, counterintuitive environmental side effects. First off, by using nuclear power, the massive pumping operation produces zero CO2 emissions. Second, flooding a giant arid region with that much water will cause massive evaporation, which actually drops the average local temperature. That temperature drop creates a low-pressure zone, which would naturally draw in humid, warm air right from the Atlantic Ocean. Incredibly, the author theorizes this cycle could permanently increase natural rainfall in the region. That means the massive pipeline itself could potentially become obsolete in the distant future once the climate is fully transformed.
Look, obviously this paper is a purely theoretical academic exercise right now, but it does force us to ask a profound question. If the math checks out on generating hundreds of billions in food and permanently healing a harsh climate, is this exactly the kind of radical, outside-the-box thinking humanity needs to finally solve global hunger and extreme drought? It's definitely a fascinating concept to ponder. Thanks for checking out this explainer with us.